Okay, let's take a look at Chapter 18, Objective 4. Objective 4 is the structure and function of red blood cells and hemoglobin. Okay, so in the previous objective, we talked about how the precursor to a red blood cell was a reticulocyte. So the formed element in blood is called an erythrocyte. It is an adult red blood cell, if you want to think about it that way. You don't have to know how many are present in the blood, but you do need to know you've got more red blood cells, then you have platelets, then you have white blood cells. Okay, so the numbers there is just if you wanted to look at them. What do they look like? What do red blood cells look like? They're not circular. They're flattened biconcave discs. So what that means is they kind of are very thin in the middle and kind of fat around the edges. They're circular, but again, they kind of go inward. It kind of looks like a donut, but it's not quite, it doesn't go all the way through. So there's no nucleus. So this is one of the few cells, platelets being the other one, that doesn't have a nucleus. It doesn't have mitochondria. It doesn't have organelles if it's a functioning adult red blood cell. Its job is to transport oxygen and some carbon dioxide between the tissues and the lungs. And its lifespan is about 120 days. Now, let's go back to the function. If your job is to transport oxygen, I mean, that's your main job. You're a package of oxygen, getting it from the heart after it leaves the lungs. It's going to go to the heart and get pumped through the rest of the body. And it's going to go deliver this oxygen to the cells that make up your baby toe. So that cell, that red blood cell, has got to be full of oxygen in order to correctly, it doesn't want to get to the baby toe and say, oh, sorry, I ran out of oxygen before I got here. I better go pick some more up for you. What is the best way? What is the way you're going to transport the maximum amount of oxygen? Well, look how large a nucleus is. If you've got a nucleus inside that cell, that's taking up a lot of space. So don't want a nucleus in there because you want to transport the maximum amount of oxygen. Think about what the purpose of a mitochondria is. Remember, that was to consume oxygen and glucose in order to make ATP, energy. Well, you don't want the red blood cell getting to the baby toe and said, yeah, sorry, I had to convert all that oxygen I had into ATP. Here's some ATP instead. And the tissue says, no, I'm asking for oxygen. I don't want ATP. I'll make my own. Thank you. So you don't want mitochondria in there either. So what happens is these reticulocytes, as they emerge from the stem cell, they're going to have all those organelles. So they're going to break down those organelles so it provides the maximum amount of space inside to deliver oxygen. So those reticulocytes are going to circulate for about the first 1 to 2 days after it gets created. And you should be able to see those again when you look under a microscope. Now, you shouldn't see many. This is way too many reticulocytes to see in a blood smear. So there's something going on with this patient. So again, they're only going to make up about 1 to 2% of the red blood cell count. So you really shouldn't see that many. Mature red blood cells, no nucleus, no mitochondria, no endoplasmic reticulum. There's just nothing there. They are to hold oxygen. The shape of the red blood cell, this biconcave disc, the shape of the red blood cell allows them to maximize volume for gas exchange while allowing them to bend and fold in order to pass through a capillary. Capillary, pretty much at this point, this blood is going through single file. And sometimes those red blood cells have to kind of change shape a little bit, be able to squish a little bit to be able to get through those very, very narrow passages to get to the other side of that capillary bed. Now let's talk about hemoglobin for a second. Hemoglobin is found inside red blood cells, mature red blood cells, and you've got about 30 million hemoglobin molecules per red blood cell. That's like a lot. So you don't have to know that number. I just find that number amazing. This hemoglobin molecule contains proteins and iron, hence why red blood cells are red, is because of that iron. Now, what kind of proteins are you going to find? Well, proteins, you're going to have 4 folded proteins, 2 alpha 2 alpha molecules and 2 beta molecules. So when you're looking over here, you see alpha chain number 1, alpha chain number 2, beta chain number 1, beta chain number 2. So you got 2 alphas and 2 betas, and each globin, each of these four-folded protein chains is called a globin, and each of those globin molecules contains a heme group. See this? It kind of looks like a frisbee, I guess, with a little red dot in the middle. This right here is that heme group. So each globin, so alpha chain number 1, this globin right here contains a heme. Beta chain number 1, this globin molecule over here contains a heme. Alpha chain number 2, this globin right here contains a heme. And then beta chain number 2, way back there, you can see that it contains a heme. So what is in this heme group? This heme group, each one of those has an iron in the very center of it. You can see all the carbons and oxygens as well, but heme, each one has iron. So there are a total of 4 heme molecules in each one of those globin structures. Let me say that again. There are a total of 4 heme molecules in one hemoglobin. So this all here, this whole thing is hemoglobin. So hemoglobin is made up of 4 globins and 4 hemes, hence hemoglobin. Now let's take a look at that heme molecule again. So you have that heme group or that heme molecule with that iron in the center. That iron is an Fe+2. Iron, the symbol on the periodic table is Fe. And that iron is capable of binding oxygen. So one red blood cell can contain, like we said, about 300 million hemoglobin molecules. And because each hemoglobin has 4 places for oxygen to bind, because there's 4 heme molecules in one hemoglobin, then one red blood cell can transport up to 1.2 billion oxygen molecules. All you're doing is taking this 300 and multiplying it by 4 to get the 1.2 billion oxygen molecules. So one red blood cell can transport 1.2 billion molecules of oxygen. That is just astronomically phenomenal to me. That is amazing. This is just some information. I'm not going to touch on it, but this is just a cool little graphic. Now, you do have different types of hemoglobin. You have this thing called oxyhemoglobin. Oxyhemoglobin, by definition, is a hemoglobin molecule that has oxygen stuck to it. So you've got this hemoglobin molecule with 4 globins and 4 hemes, and it's got oxygen attached somewhere in there to one or all 4 of those hemes. That's oxyhemoglobin. The binding of oxygen molecules to hemoglobin occurs in the lungs. Remember, when you inhale, you're inhaling oxygen, and that's at that time, that's when that oxygen can get stuck to that hemoglobin molecule. If you remember what we said previously, when you have oxygenated blood, that's going to be that bright red color. Because again, oxygen is attached and changes that iron +2. Deoxyhemoglobin. Well, you can probably figure out by the name what this one is. This is a hemoglobin molecule that does not have oxygen stuck to it. So this would be after it just dropped its oxygen supply off at the tissue level. The tissues say, hey, we're hungry for oxygen. And the red blood cell says, here's my oxygen. You can have it. I brought it to you. So when it does that, when it releases the oxygen from the heme molecule at the tissue level, that hemoglobin is now deoxygenated. So it's called a deoxyhemoglobin. And again, the color is going to change. That's going to be a dark red color. And that's why the blood in your veins, because it's carrying deoxygenated blood, is going to be a darker red than that bright red blood that's going to be found in the oxygenated arteries. There's also another kind of hemoglobin. It's called carbaminohemoglobin. And this is a hemoglobin molecule that is transporting carbon dioxide. So remember when the venous blood, the blood in your veins, gets to your lungs, it will let go of that carbon dioxide molecule. So when the blood is in your veins, most of it is carrying carbon dioxide because it just dropped off the oxygen in the tissues and picked up the waste, that carbon dioxide. It's going to carry that carbon dioxide from the tissues back to the lungs where you will then exhale. When the carbon dioxide is bound to the hemoglobin It is called carbaminohemoglobin. And again, this occurs when the tissues drop off that carbon dioxide as the red blood cell is passing through, to get rid of that waste. Just FYI here, carbon dioxide actually binds to the globin part, not to the heme part. This is just showing you the different places it binds. There's actually conformational change in the hemoglobin molecule. You don't have to know this. I just find it very interesting. Again, carbaminohemoglobin, you can kind of see here that carbon dioxide is not binding to the heme and is binding to the globin part. I do want to mention carbon monoxide. Carbon monoxide. If you ever heard of carboxyhemoglobin. So what happens is, for instance, if someone is cooking on a camping stove inside their house, let's say in a non-ventilated area, what happens is when there's not enough oxygen present in the environment, you get carbon monoxide formed. And that's why they have like carbon monoxide detectors for homes and things like that. Carbon monoxide is odorless, so you're not going to know it. But what happens is when carbon monoxide is present, it actually really loves to bind to red blood cells. To be honest, the hemoglobin loves the carbon monoxide. The hemoglobin in the red blood cell loves the carbon monoxide more than it likes oxygen and carbon dioxide. If it has a choice, if your hemoglobin molecule has a choice between, do I'm going to grab the carbon monoxide, the oxygen, or the carbon, it's going to grab the carbon monoxide every time. It'll pick that over oxygen. So this carbon monoxide, notice right here, binds very tightly to hemoglobin, so much so that it doesn't even want to let go. That's why people that get carbon monoxide poisoning, they can die from that, because your red blood cells, if you get them into fresh air and things like that, your red blood cells are really hanging on to that carbon monoxide and don't want to let go. So even though you provide that fresh oxygen, the red blood cells really are like, nah, I'm kind of happy with this carbon monoxide I got stuck to me. I'm good with that. But that's called carboxyhemoglobin. Now, 2 words, again, you're going to learn about these later on in the PowerPoint as well. Anemia is ineffective hematopoiesis due to insufficient numbers of red blood cells. So when a person is anemic, the one thing that could be happening is they're not making enough red blood cells, resulting in ineffectively delivering oxygen. If you don't have red blood cells, then you don't have enough hemoglobin, you don't have enough oxygen. So we talked about this previously also in this unit. Anemia means you just don't have enough red blood cells, and you can see that in a hematocrit. Take a look at the volume of red blood cells. Remember, it's supposed to be about a little less than equal to the plasma. On the reverse of that, polycythemia is an overproduction of red blood cells. This is where, again, you're supposed to have about equal, a little bit less, right? But here, your red blood cell numbers are higher, much higher than the amount of plasma that you have. Polycythemia, elevated hematocrit. Percent saturation. This is, by definition, the percentage of hemoglobin sites occupied by oxygen in a patient's blood. You can detect that by a pulse oximeter. Normal is 95 to 100% saturation of blood with oxygen. Now, if a person is hypoxic, they have low blood oxygen. And again, this is detected by the kidneys. And when the kidneys detect low blood oxygen, they will secrete erythropoietin. And then that will then eventually get to the bone marrow, where the stem cells in the bone marrow will say, oh, EPO is present. I should start making some more red blood cells. So again, your kidneys, your tissue oxygenation decreases. That's going to cause the kidneys to secrete EPO. That EPO is going to end up going to the target cell, the hematopoietic stem cell, which will then make more red blood cells. Factors that cause a decrease in oxygenation, like we said previously, anemia. If you don't have enough red blood cells, then you're sure not going to be carrying oxygen. Low blood volume. If you don't have enough blood volume, if you don't have enough hemoglobin or iron, if your blood flow is poor circulation, or pulmonary disease, any of these can lead to a decrease in that tissue oxygenation going through the kidneys. Life cycle of a red blood cell. So again, you believe it or not, this is amazing. 2 million red blood cells are produced every second. If you're going to make red blood cells, what kind of ingredients do you need? Well, you need sugar, glucose, you need lipids, fat, amino acids. Those are the building blocks of protein. So you need those three. You need iron. We said earlier that iron was at the center of every hemoglobin molecule. Um, there's 4 irons in every hemoglobin molecule, copper, zinc, and some B vitamins. So we didn't really talk about those last 3. So these are erythrocytes. These red blood cells live up to about 120 days. And like the other cells, they are destroyed by macrophages. They're a phagocytic cell in the bone marrow, liver, spleen. So as the blood passes through there, if that red blood cell isn't functioning the way it should, it will be tagged for destruction, and the macrophages in those locations will then destroy that red blood cell. And you can see these red blood cells here, biconcave discs. Erythropoietin stimulates the production of red blood cells in the bone marrow. Reticulocytes, precursor to a red blood cell, enters the bloodstream and they mature into red blood cells. Remember, they last for about 1 to 2 days, and reticulocytes come out with organelles. So it gives them about 1 to 2 days for them to destroy all of those organelles, and then they are a functioning red blood cell. And they will then circulate for about 120 days. Worn out red blood cells pass through the bone marrow, the liver, and the spleen, where macrophages break down the red blood cell. So macrophage is a type of white blood cell, and it phagocytizes, it engulfs that red blood cell. So those red blood cells are targeted for destruction. The macrophage doesn't make the decision and say, oh, you look good, or oh, you look old. It's tagged. That red blood cell is tagged, so macrophage knows which ones to attack. The globin, what do we do with the globin? Remember, that was a protein, right? 4-folded proteins. You got alpha 1, alpha 2, beta 1, beta 2 chains. That protein, that globin, is broken down into amino acids and will be used to build more red blood cells later. So everything is recycled. It's really amazing. Iron is sent to the liver or spleen to be stored and used later to make new red blood cells. This is why your liver and spleen are dark red, because that's where the iron is stored to make more red blood cells. The remaining components of the red blood cell get converted into a substance called bilirubin, where it travels to the liver and is used to make bile. That bilirubin will be used to make bile, which is going to help break down fats in the digestive system. Bile ends up in the small intestine and gets broken down into a substance known as bilirubin. So the bilirubin gets converted to bile. The bile then goes back into bilirubin in the small intestine. And then the bilirubin will either, once it's in the small intestine, will stay in the intestines and pass as feces, or enter the bloodstream, make its way to the kidney, where it will be eliminated in the urine. So the bilirubin will not go back to the liver to be made into bile. So bilirubin, it will that red blood cell gets that old damaged red blood cell part. Some of it gets converted to bilirubin, but then once it gets made into bile and gets reconverted back into bilirubin, it will exit the body either in feces or urine. And I just wanted to remind you guys, we talked about it previously in AP1. I just wanted to kind of show you guys about a macrophage. We've got a white blood cell here, this macrophage, and inside it's got those digestive enzyme organelles called lysosomes. So you've got this virus that's being engulfed. Notice it's now inside the cell. These lysosomes will bind with the foreign particle and break that foreign particle down into pieces and then spit out the waste. This is just showing you a picture of the life cycle of a red blood cell. Okay, I'll give you a second from those in-class questions that you have in your packet to take a look at set 4. Okay, should be 120 days for the lifespan of a red blood cell. And what organ breaks down old red blood cells? Liver. Now, keep in mind, that was the liver, the spleen, and the bone marrow. So any of those could have been the right answer, but I didn't have those other 2 as an option. So again, be sure to read all questions. I'll give you a second to take a look at 3 and 4. Okay, number 3, iron is in the center of the heme portion of the hemoglobin molecule. And then carbaminohemoglobin is going to have carbon dioxide attached. Carboxyhemoglobin was going to have carbon monoxide, and then oxyhemoglobin would have the oxygen. I'll give you a second to take a look at set 4. Question 5. Bile. Okay, and then bile will then go with the food into the small intestine where it gets converted back into bilirubin. And that concludes objective 4.